the last talk before we have a fantastic reception. And yes, it will be a little bit shallow, though it's about deep learning. So those of you who are experts don't go to sleep, because you can, whatever you know more than me, we can always discuss later on. So I'm with the Center for Data-Driven Discovery at Caltech and the Astronomy department. And what I'm going to do is give you an intro to deep learning with some examples in astronomy and maybe a couple other fields. But the way deep learning has progressed, I have to start with some examples that are non-astronomy. So let's get going. So what I'm going to do is some of the background that was there before deep learning. What is it that goes under the hood, even below deep learning? Some flavors of deep learning, like the convolutional neural networks, the recurrent neural networks, and so on. Some of our work that we have been doing with these things, a few resources and roadmap, and especially the pitfalls and progress we hope to do, we meaning the world hopes to do in this particular area. So again, very briefly, many of the earlier concepts came about because of the neural network within our brain, and a single neuron, it has many dendrites that come together and get connected to the axon. So it is the activations on these individual dendrites and the amount of signal on them that get added and that get passed on to the axon. So similarly, the simplest thing that you have in a neuron would be there are many inputs that go in, and then there is an integration that happens with them. There is a response which corresponds to an output. So this is how an artificial neuron then looks like. What you have here is that several bits of inputs, and then you have got various weights on them, and then it is summed here. Now normally you normalize them, because normalization is very important, and you have to make sure that they are not going all over the place when you bring in different inputs. And then the other important thing is that you have to also normalize the output that you get. So there are 2 or 3 different functions that are typically used for that, because once you sum up all the different inputs, even if originally they were normalized individually, the sum can be very different in different cases, and having them normalized is a crucial thing, so that should never be forgotten. So this is how typically the weights are then changed. You have got these input weights here, and based on what has happened. So this is part of the supervised classification typically. You know what the object that has gone in is, and then you get an output. If the output is the same as what you expected, you are generally fine. But if it is not, then clearly the weights are not doing their job. So you go back and change the weights. And this is the recipe for the change of weights. This row here is the learning parameter. So that cannot be too big, otherwise there is a huge oscillation in the delta W's that you have. And T and O are, O is the output and T is the input, and then Xi is what the Xi's are here. So the delta Wi's are the important things. So as you keep on changing them, the weights settle down to correct results. And what was said earlier, Paulus mentioned during the training part, for instance, is that you have to keep a set of objects aside on which you are going to validate things. Those set of objects should not be seen during the training. Otherwise, what's going to happen is that your output classifications are going to be biased by the network seeing what you already have. And so these are 2 or 3 different types of activation functions that are typically used. This is sigmoid, where your input can vary over a great range, but the output goes from 0 to 1, typically a good normalization. There is the tanh, which is used in many cases, where again your input range is huge, but the output now goes from -1 to +1. And ReLU is used extensively in many, many convolutional neural networks. What you have there is that the input can be again a wide range, but everything below 0 is converted to 0, and then the rest of it can stay to the positive range that it already was. So depending on what application you have, you can use some of these. For instance, in the recurrent neural networks, you see a combination of tanh and sigmoid and also ReLU, but CNNs often more people use ReLU. And especially the number of libraries that are out there, the number of canned examples that are out there, ReLUs get used. So most people who are new to deep learning simply take that code and start using ReLUs. So that has become more standard, more of a standard because of that as well. So there is a effect that goes in. And I'm not sure what happened here. It was certainly not Planck. And, now everything's Planck. Yeah, No, sorry. You mean there? Yeah. Yeah. Hmm. And the first few slides are fine. Yeah, I do. Let me get it from here. Really? How did the first ones stay there? It wasn't a large one. Let's see. It's the, maybe that one will work. What is that one? Yeah. Mhm. No. What about that one? Is it the same one on the other side? No. So this doesn't work with mine. Yeah, that should work. It's not a USB actually. This should work. Is this the right one? Yes. Okay. Okay. Good. Yeah, sorry for that. Okay. So MNIST is one of the earliest and most extensive data set that has been used typically before the days of ImageNet. And here what you have are many, many handwritten digits and many different examples clearly written by different people. And so what you see on the left-hand side is a single one, and it is a 28 by 28 matrix, and you can see numbers between 0 and 1 representing that one. And so this, when you convert it to a long 1D thing, you get many zeros and ones. So you can put a threshold here or convert them into zeros and ones. And then what you do is that then you can input it to this thing that we have seen before. You do the summation as was seen before, and what you're going to get is a one hot output. What that means is that whatever was the digit as input, for that particular digit you will see a 1, for the others not, when it's working fine. Otherwise what you do is that turn around and give the feedback as before. So this is again another way of just showing that you have these 0 to 10 coming through. And when you have these layers, they are essentially working like joint probabilities. So you're trying to combine these things, and you can add multiple layers, and then there will be additional sets of weights that are coming through, and they keep on getting added. So you can have information flowing back and forth where the weights get adjusted and you get better and better classification. So these are the restricted Boltzmann matrices networks. What that means is that within a single layer, the individual neurons are not connected to each other, but typically all neurons of one layer are connected to all neurons of the next layer. And so if we look at a simple thing in astronomy, if we wanted to construct, say, a classifier that uses just the distance from the plane of the galaxy, our galaxy, and the distance to the nearest galaxy to say whether a given transient is extragalactic or not, you can just have these two inputs. You have a matrix 1 by 2, you have some weights, you have a hidden layer which has 3 neurons in that, so 2 by 3 matrix, this should be 3 by 2, 3 by 2 matrix, and the output is whether something is an extragalactic transient or not, just based on these two things. And you can have a set of objects, train it, and this will start giving you output related to that. And so the thing that is used is that the weight cost function is used, j f of y minus y prime. Again, one is an output and the other is what you are getting. And then you can reduce the cost by adjusting the weights, where now there are multiple gradients here because of the set of weights you have. And so gradient descent comes into picture, and those are the basics that go into this. And so what happens with CNNs is that this is like a mapping between the two, but in the case of convolutional neural networks, there are many, many filters here, and it starts getting wider and wider and a little bit smaller, and there are certain operations because of which that happens. So those are the ones that we'll be seeing. So this is essentially a single slide primer for convolutional networks. What you have got is the input image. And now instead of taking the entire image, what happens is that you take a small portion of it, and that portion is now convolved with a given kernel or a filter, and that gives rise to a new image here. And then you can have multiple such filters, multiple kernels. So each of them will give rise to a new image. That is why you see this stack of images here. And this is a typical kernel here. So here's it is along the diagonals. So the diagonals are highlighted and the middle parts of the edges are zeros. So what this kernel is going to do, it's going to look for elements that are roughly diagonal. And so that can be seen here as we progress. Okay. So what this is doing is that convolution is happening over 3 by 3 regions, and then it is marching through that, and you are getting an output matrix here. And then the second layer typically is the pooling layer, where what is happening is that it is just reducing the size of the layers. So you could do a pooling by 2 by 2, 3 by 3, and so on. In this case, it is a 2 by 2 pooling. So what is happening is that, and it's a max pool, so these 4 elements are taken, the maximum of that is taken and put here. Similarly, the next 4 elements are taken and that go there, and so on. So that reduces the dimension of each of the output layer by a factor of 2. And then this is also great for transfer learning. What can happen, and this was the question that was asked at the end of Paulus's talk, that this was not the one that he has used in his talk, but can be used. So if you have trained a network through up to the last layer, so the weights have now settled with whatever input set that you have provided, what you can do is that you can take your own data set and train only the last layer, and then be able to get reasonable results. And that's the kind of transfer learning that many people are trying out. So there are these wonderful networks like AlexNet, ResNet, VGG16, VGG19, and so on, where large computers have trained them over several weeks typically. And what you can do, you can simply take the model with the settled weights, use your own input data just on the last layer, add that layer, and then start getting results out. So how is it that these filters are working? So if you take a simple filter like -1, 0, and 1 and treat this as your convolutional kernel and pass it over the chair, what it's going to do, it's going to highlight over the vertical what the edges are, and that is why you are seeing these edges here, right? And so essentially what is happening there is that features are being extracted through convolution, and the more kernels you have, the more kinds of features that you can extract. So during the first layer, what happens is that you get the simplest of features like edges, verticals, diagonals, and so on. And by the second layer, you start combining those into more complex features. And so again, cats and dogs were shown before. It is what was done quite early on as an example. So in typical ML, what happens is that you have input, there are features that are extracted, then there are these features, and then with the ML you get an output. Whereas with deep learning, what happens is that you start with input, there's the deep learning algorithm, and you get output. So essentially, again, in this case too, getting the features is eliminated, or it does the extraction of features internally. And the slight difference is that it gets millions of features, and in that very large dimensional space, that magic is done. And that really seems like magic, and that's why, though it seems to work better, one of the pitfalls is that it is a much blacker box. And trying to understand how it works, how it goes about doing that, is one of the burning questions of the field. So this is how convolution looks in 1D, and this is how it will look in 2D. In astronomy, of course, we are familiar with what convolution is, because all the light that comes from outside the atmosphere gets convolved by the atmosphere, and we get our PSF. It's just that in this case, the convolution is specific kernels, specific filters that you have designed, or someone who has written the library has defined, and those are the ones that we are using it. So there are many, many hyperparameters that one gets to use with these. And this is again a big pitfall because many people use the convolutional neural networks out of the box. They simply take something, use some standard parameters, and that gives them some results. But there are many ways you can do it far, far better. So there's the depth of the network, there's a stride. We looked at how the convolution could go on. You could say when you do a 3 by 3 filter, you could take the first 3 elements and then directly jump to the, say, the 4th, 5th, and 6th element rather than the 2nd, 3rd, and 4th. So there are ways you could change that. Then there is padding. After you, if you are doing a 3 by 3 convolution, then the first element or 2 element, depending on how you are doing it, are going to go away. So the age is going to away. You can pad them with zeros to have the same dimensions and so on. Then the learning rate can be changed. The number of epochs can be changed depending on how deep you want to go. Batch sizes, so you don't have to give all examples at a time, and people typically use batches of smaller sizes, say 16 or up to 128 and so on. And the activation function can change. Weight normalization can change. Again, we are using gradient descent, so we want the gradients to be small, but not so small that they vanish, because zero gradients can be a big problem in some of the networks. And then the dropout rate. We don't want overlearning to happen because that is another fear. So when you have a dropout rate of, say, 0.25, that means that your neurons are learning, but then randomly you let a few of those go, because then what that makes sure is that not the same ones are coming through a large number of times and you are overlearning your example. And there are ways to do things using Bayesian also, and of course that takes much more training. It takes much longer time, so it's not used as much, but there are people who are trying to optimize that as well. And then there are grid and randomized searches that are used also to go on. So this is how filters features get built up. So when during the first layer, what you see are the simplest kind of features, here again linear and so on. And this is again the ImageNet set, by the way, so it is all terrestrial images. There were 1 million plus something. And so when you go to the next layers, you can start seeing more and more complicated features. And by the time you have reached 4th and 5th layers, you can see parts of bodies, parts of objects, and entire objects being assembled together. So that is how things build up. So there is a promise that there are new features that are coming into the picture here, because it is looking at millions of features. But then how to make sense of that is a big, big question. So this is the main thing about CNNs. There's another kind of deep network that is being used a lot now. These are the RNNs. Again, these were mentioned a little bit earlier. So these are the recurrent neural networks, and a form of that is the LSTMs, which are the long short-term memory networks, and a particular type of them called the GRUs, the gated recurrent units. So what happens in LSTMs is that you can input to it a time series, for instance, or a sequence of events, and the output of one part of it gets fed into the next one, and the output of that goes into the next one. And essentially there is this logic that is here that makes it interesting, and one can use it to configure for time series as well. Here what is happening is that one is deciding what part of the input goes straight to the output, then whatever you may have learned from before, what part of it should be dropped, and then what new things should get added to it. So that is what these three things that are here. So some part goes straight away and you are modifying things. So this is then able to combine together bits from before, new bits that you run. So for instance, if you have, say, a time series coming through and you are more interested in the peaks in that, you can train the network to keep the peaks. But then you can also have the logic such that keep the peaks only if there is a difference of, say, 1 magnitude, not if it's less than that. That way you can keep track of specific peaks and so on. So it has been used extensively for sentence parsing in English, for instance, and the same would work for time series, except that if it is a time series that is regular, it's going to work far better. And when it comes to astronomical time series, the same issues come about, that these are irregular, then they are heteroscedastic, and using them properly in that fashion is not a straightforward thing. But there have been astronomers who have used it in the past, and I'll come to a couple of examples. AlphaGo has been mentioned before, so I won't go into that more, but it's again a complex deep network where there was depth as well as there was width here, and as George mentioned earlier, AlphaGo was able to beat the best Go player, listed all 4-1, and then there was another network that was able to beat that network 100-0, learning only from the rules. So what is happening is that these learning from given data sets, if the data sets are good, is quite good. So the way the initial learning was done, these are the different kinds of recaptchas that we use all the time, where many times you have to identify two things that are alike, and typically one thing is already labeled, and so they already know that you are doing it correctly, and when you give it a second one, they're learning it from there. So this was one occasion when Facebook for some reason could not give my images though the page was loaded, and I was able to see the actual description of the images that I had for my cover page and for my profile picture. So they do have these bag of words that you can see there which represent each image, and that's how when you search on things you are able to get to those. And of course searching for individual images is straightforward, but what one can now do is also search for multiple things in the same picture. And when you start doing that, you can understand how the attention of the network is in different places and it is able to do various things. So again, what is important in most of these cases is that very large data sets are needed, labeled data are needed, metadata is very important in many of these cases, and if peripheral data are available, that's very good. One other thing is that the data sets have to be balanced, because again, if there is imbalance, then what's going to happen is that the network is going to give you fantastic accuracy by calling the most significant set as the classification in each case, and you don't want that to happen. Generative networks were mentioned before, and they are getting better and better as well. So if you ask the setup to give you a white bird with a black crown and yellow beak, the first set of images can come through which look roughly like birds, but you can make out that they are not really the kind of birds that you are looking for. They do look artificial. And again, these came out from the network, not from examples that the network had seen, but generated by the network. And once you refine that a little bit, the network is able to come up with the second set here. So those are realistic looking images. But the question to ask is, so here our brain can be fooled by that. Our mind can be fooled by that. But when you generate similar data sets in astronomy, again, we can be fooled, but how close are they likely to be reality? So those questions are quite important. Other cases where these networks are being used is where face detection we all know about, but here in case of these Google virtual reality, not virtual reality, the Google, what is it called? Sorry? Yeah, Street View, but Street View combined with they have the viewer in which you can look at those things, so you can go to various places. They're masking the faces for privacy, and that's a fantastic use, I think. Again, deep learning is what is behind that. So ImageNet has been a great thing with all this, and what has happened is that over the last few years, the error rate has been going down and down with improving things like AlexNet and GoogleNet, and it was in 2015 that it fell below the human error rate. What that means is that not only are these faster than us, but they are making less errors than humans at recognizing terrestrial images. And here is a demo that you can use this from Berkeley using Caffe, one of the libraries. You can go there at some point and fit in some images, and it gives you classifications directly. So coming to astronomy, in 2015 there was this paper by Dielman et al. Where they did galaxy prediction using CNNs, where it was rotation invariant. So they took a set of galaxies, rotated them, flipped them, did all kinds of things, and were able to separate galaxies in different ways. Then Guillermo's paper here on hits about separating artifacts, deep hits was there, where there were two types of objects, real objects and artifacts. Those were fed into these networks, and they were able to classify them as well. Also, Fabian is not here, I guess, so they have also done a little bit of work on similar things, separating artifacts. So these image-based applications are really proliferating. There are lots and lots of cases, for instance, with gravitational waves, noise characterization, or bars in galaxies, or for radio galaxies, star galaxy classification, and many examples. They are growing really fast. Again, what one really needs are a lot of examples, and well-labeled examples to start with. And then in many cases, augmentation of data may be required and is possible. So for instance, if you don't mind the galaxies being rotated, because in the universe you see both kinds, that's a perfectly good thing. You can rotate them to have different angles and so on. You can scale them in different ways, because galaxies at different redshifts can be seen in different ways. So all that is possible, and wherever that is possible, it's useful to do the augmentation and go about doing that. So coming to non-image things, again, RNNs have been also used in astronomy. So there's this paper by Charnock and Moss which use supernova challenge light curves. But here the examples that they had to use was tens of thousands. And then if you had fewer examples, then they found that it was not a very good classification that they were getting. There's another paper by Naul et al. Where they have used encoders and decoders to do, again, similarly classification of light curves. We have been doing a little bit ourselves with LSTMs. This is a work with Shreyasi Das from University of North Carolina. So there again, a little bit of domain adaptation, transfer learning, just like what Paulos was mentioning. So coming to one of our own applications of TMDT, where what we did is that try to combine the two, where we had time series, but we didn't want to use the time series as such, because in LSTMs, one has to do a lot of configuration, and because of the large gaps, one is not really sure how well you are doing. So what we did is that we decided to convert the images. We had about 50,000 periodic variables, one of the kind of data sets that Paulos mentioned that we have been using a lot, and we need to diversify it, make it bigger, and so on. So what we did is converted the time series into an image and then use the CNNs with that, so that though we had time series, we could go to the other way. Matthew had showed this picture. So if you take pairs of points here, the x-axis defines the delta t and the y-axis defines the delta m. So you go to this rectangle here, a mapping where the bins are of different size, because we use the CRTS cadence where we had images that were separated by 10 minutes each. What happened is that these are very uneven bins, and in that uneven bins, then they get mapped to these even sized pixels, and those even sized pixels then become the input for our convolutional neural network. And we had a fairly unbalanced class where the first class had something like 60% of all the examples, and we used at least 500 examples from here. One thing that happens with this framing is that here we are not rotation independent, in the sense that the axes are fixed. So the middle part is where the delta m is 0 and so on. So we had to use them as it is. And we started using it with this convolutional network with 3 layers, and then we got fairly good accuracy, which was roughly the same as random forests. And again, what that means is that without getting any features out of our time series, we're simply able to classify them as well as random forests. So that's good. And then we were able to reduce the depth of the CNNs, and we're able to get similar results. So these are some CMs, and I won't go into those details. So again, let me skip this part for brevity. So this is more like going to a street, and there are some cars on the street, and each individual object is like perturbation on the empty street. And so what one is trying to figure out is how the street itself looks without the car. So that's the analogy that we could use for our CNNs. And then we also found some surprises within our thing. So our first class, there seems to be possibly 2 subclasses. So that is something that we need to look at more closely. And then another example that we have is where we are looking for transients through direct image subtraction without going through the standard stages. And Nima, who's here in the audience, is likely to be speaking more about that, so I'm going to skip that part. But just to show that this is another encoder-decoder network where we used directly images, went down to the transient representation, and then from that build the original images to figure out where the transient should be. This is the network here, so won't go into more details of that. Another thing that we are doing is with deep learning is using streaking asteroids. So these are nearby asteroids that leave streaks. This is from ZTF, so we have many different possible examples. So there are satellites, there are cosmic rays, there are flashes from glints, and real short asteroids, and as well as some other kinds of artifacts. So we are using this in combination with Zooniverse to mark objects and giving this to a deep learning network. We already have some good results. I won't go into those either, because this is again a straightforward application. In terms of methodology transfer, we are doing something similar with some of the cancer data sets. Here, for instance, we have 50,000 heavy smokers followed over several years, and some of them developed cancer and some of them did not. And we are using in a fashion similar to the previous examples that I mentioned, using images that for these lungs. So what has happened is that radiologists have previously done classification on these, and there were 98% false positives. That's a really large number, and there are many reasons for that. Even the radiologists sometimes don't agree with each other, but that's something that we are hoping to reduce for this. And again, we are using some Zooniverse setup to go with that to get some augmentation of the data sets that we have. So here are some of the reasons why deep networks have proliferated. There are faster computers available, there are cheaper and better GPUs, but computing in the cloud has gone a big way to do that, because people can easily spin up GPUs by having a few dollars or a few tens of dollars or a few $100s, and that's been a big boon. So libraries that go with that have really, really helped get things. And then the availability of data sets like ImageNet and MNIST also, because there are standard examples. And I'll quickly flash an example. We don't have to go through it, but it'll be in the slides. So there are just 20 lines of code where you can use that to go through quickly. And again, several libraries are available, TensorFlow and MXNet. TensorFlow has been around for some time, and they're adding more and more tools to that. It's getting better and better, especially combined with TensorBoard, which allows you to do lots of visualizations. And MXNet, which AWS has been pushing a lot with their Gluon library. Again, it gels very well with the AWS setup that you have. And Keras is great for visualization, and you can combine it with a bunch of things. So again, AWS that I was mentioned. So here are a few lines of code from TensorNet, TensorFlow. You can easily start loading libraries, use various steps that are in there. So these 10 lines and these 10 lines, you can just input them and you start getting up 90+% accuracy easily. And then it's a simple matter for you to take your own data set, switch that in instead of the MNIST data set, and see what kind of accuracy that you get. And again, MNIST had 10 classes, so it is a multi-class classifier, so fairly trivial to go and do something like that. So in the next few minutes, what I'm going to do is talk a little bit about the issues that this whole field faces and where we can be going from there. So it's very good that Paulos showed that example of lion and tiger and an ostrich there. So here is a similar example, but here what you see are there is a school bus, there is a quail, and there is a temple, and we can clearly see that. And then what the researchers did is that they changed a few pixels, some specific pixels, and then what happened? It continues to look like before. But now the network calls all these three specifically an ostrich, and I don't know if it's just a coincidence, Paulos, that you had the ostrich there, but okay. Like the quail, right? Yeah, okay. So the network starts calling it ostrich, all these three images. So what has happened is that specific pixels, which are the ostrichy pixels in the images, were used by the researchers, and those pixels were modified in the three images, and that is how we get those. And that is what is seen in the MNIST here. So there is some kind of a saliency that you see in those images, and that's what one has to go after in order to understand what may be happening here. So interpretability of deep networks, that is a big thing that one needs to look at. And so what we have here is, if you have got this network, then you can, when the network calls it a cat with a probability of 93%, why did you do that? Why not something else? Then when do you succeed? When do you fail? When can I trust you? How do I correct an error? All the questions that one can ask. And then tomorrow, this slide from 2016 from David Gunning in a DARPA meeting. One should be able to say that this is a cat because it has fur, whiskers, and claws, and it has such and such feature. And then you can rely a little bit more on whatever you are getting from your network. So that's where we should be going. And looking at the tools that currently exist, what we have is the decision trees are something that we can easily explain because there are specific decisions that are happening. And as we go along, random forests are here, less explainable, but they have a better prediction accuracy. And by the time you reach deep learning, they're far better at predicting things, but we hardly understand anything. But that's where we need to get into. We need to start understanding that a little bit more. And with things like TensorFlow, one can get into visualization, so you can have many distribution summaries. It's more interactive, so each of the button is like a workflow. You can push a button and start seeing many different things there. So for instance, there are various view options that one can see. So we've been doing some experiments with visualizations for interpretability using Keras visualization. And there are three kinds of things that you can easily do. One is activation maximization, where if we call this A, it looks at the inputs and an intermediate layer here, because what's happening is that generating input images that activate later filters. First filters, it's easy to visualize what is happening, but it's not so easy to look at what is happening at the later filters, because the inputs there are the intermediate filters. So this allows you to do that. Then saliency maps allows you to understand the gradient of output category with input image. So how the category of the output changes with respect to the input images. And the third thing is class activation map, where the spatial information is still intact here when you go to the first fully connected layer, how things are changing there. And then you can start seeing here how those would look. And here with our DMDT examples, these are two classes, one of the eclipsing classes and one of the RR Lyrae. And here in case of the eclipsing class, for instance, what it sees is that the network seems to be paying more attention to pixels where to the blank pixels rather than where there are pixels. So somehow it's giving more attention where there is no information. That is, this may be looked at as the complement of the information, whereas in case of RR Lyrae, for some reason it is looking at areas on the longer periods, whereas the RR Lyrae themselves have a shorter period. So these are the kinds of things that one needs to look at, and this is the saliency for some of the same classes. So these visualization are something that's going to be crucial as we go ahead. But then there is a set of people and some very influential people who are saying exactly the opposite. And this is a quote that Jan LeCun has invoked more than once. This is from a 1987 paper, which reads that when a network is given more resources than the minimum needed to solve a given task, the symmetric low-order local solutions that humans seem to prefer are not the ones that the network chooses from the vast number of solutions available. Indeed, the generalized delta method and similar learning procedures do not usually hold the human solutions stable against perturbations. And we have seen something like that emerging also from some symbolic regression works, where when you give it a problem, it comes up with solutions that are fairly complex and they don't seem to make sense, but clearly that is the best solution that the system has come up with within that period, and it seems to work roughly to the same level as other solutions have worked. Just last week we were in Chile, where we gave a set of students a problem. Matthew was supervising that, and they were looking at Sloan magnitudes and colors, and it turned out that besides the GRI filters, two of the important parameters were the U and the U minus Z, which normally don't come up for photometric redshifts. So and then the formula was of course complex with many things, U minus Z times something, something, several terms that came in, and the plot looked reasonable, right? And so there are likely to be things out there which are fairly more complex, and I'm not sure whether we should demand explainability every time. If it works very well, including proper validation and proper test cases, then many times one should be able to accept that. But at some point with bigger data sets, then trying to understand it may still be good for our own sanity perhaps. But I think that is where one may have to leave it for now. So I'm going to leave you with this summary that deep learning is showing up in many, many different garbs. It's getting better and better, again, for the reasons that I told you about computers, libraries, computing in the cloud, and so on. There are many applications already out there in astronomy, but it's still not been explored enough. There are many more possibilities that are out there, especially things like transfer learning and so on, with all the different data sets that are out there. Most groups use only a limited number of data sets. And many times if you own a survey, if you run a survey, you tend to use more of that, ignore many other surveys. Thankfully, that is changing now. For instance, as Matthew mentioned, with ZTF, we are going to be using the older surveys like CRTS, PTF, but as well as other wavelengths and whatever we can lay our hand on to try to get a holistic picture there. And interpretability is important, but it may or may not be possible, and we'll have to see where we can go with that. And I'll stop with that. Thank you.